Question 3, Part A. The rate of reactions between 2-chloro-2-methylpropane and methanol is investigated. When there is a large excess of methanol, the overall reaction is first order, means methanol will not really contribute to the orders, and now the orders of the reaction is just depends on this one. The 2-chloro-2-methylpropane means the order for this 2-chloro-2-methylpropane is the first order. And figure 3.1 shows the results obtained. Okay, this is the half-lives. Okay, we will discuss later. Part 1. Use the graphs to determine the rate of reaction at 40 seconds. Show your working. Okay, first you have to understand this is not really a graph paper. What you can do is just a rough estimation. You try to draw a tangent at this time equal to 40 seconds, and you try to get the two coordinates here on the axis y and x. So because it's not really a graph paper, so we can just roughly estimate. So for example, if let's say now from this we can use 0.01 over 85.5 second. So means the rates roughly you'll get 0.000171. So the rate is this one, mole per dm cube per second. Okay, just calculate like this. For part 2, use the graph to show that overall reaction is first order. Explain your answer. So first order, we know that the half-life must be almost constant. Means you have to identify or get the half-life. So this reaction is started with this 0.02. Half of the concentration is 0.01. And after that, you try to get, okay, you just draw one line, okay, to this point, and you get the time. So roughly you get about 30 seconds. Just roughly, we cannot really get the actual one, about 30 seconds plus minus. Okay, after that, from 0.01 to 0.05 is halved. So half of the concentration. And here you draw one line and touch the curve and get another time here. So just now here is the first half-life, and the second half-life is this point minus this point. So this is the second half-life. So as you can see from this graph, the two half-life is actually quite close. They are quite similar. So we know that this one is a first order, or actually we can prove that this is a first order because these two half-life, they are quite similar. Right? This is a characteristic for the half-life. For the first order. When a reaction with first order, so the half-life must be constant. So therefore your answer should be like this. From the graph, the first half-life and second half-life is around 30 seconds, plus minus. Therefore, the reaction is first order because the half-life is almost constant. That's how you prove that. Part B. In a different reaction, which is also the first order reaction, 75% of reactant is consumed in 220 seconds. So this one you have to understand. 75% of reactant consumed means 25% remains. So from 100% to 25% is go through two half-life. 100% to 50% first half-life, 50% to 25% second half-life. So means it need to go through two half-lives. And To calculate the rate constant for the the reaction with first order, so we use this. The half-life equal to 0.693 over the rate constant. So rearrange. So rate constant therefore is equal to 0.693 over the half-life. So do not use the time that given, you must halve it. So don't just direct substitute this one to this, right? So because it's go to 2 half-life, so the actual half-life is 160. So means it's 0.693 over 160. So you get this 4.33 times 10 power negative 3 per second. Part C1. Define standard electrode potential. Standard electrode potential is the difference, potential difference when a half cell is connected to the standard hydrogen electrode under standard condition. So what is this? Means we use the standard hydrogen electrode to get the potential of others half cell. Okay. For example, we use this drawing. This is the SHE, standard hydrogen electrode, and this half cell is connected to this SHE. Because SHE itself is 0 volt. When one half cell connect to the SHE, we can easily get the potential of this half cell through the voltmeter. In this case, this half cell, it will show 1.33 volt. So this is how we get the standard reduction potential for the any half cell, or the potential of any half cell, right? Just by comparison, compare with SHE. Again, this one is potential different when a half cell is connected to standard hydrogen electrode. Okay. So part 2. A short bridge is used in an electrochemical cell. State the function of the short bridge. Explain your answer. So of course, the short bridge used is to balance the charge. So ion move from the short bridge to maintain the charge balanced or complete the circuit. Very easy. We use back this drawing. If let's say now we have this KCl as a short bridge material. So we know that the SHE, when it's linked to this half cell, the potassium dichromate half cell, so this one will be a negative electrode. Later we discuss what is that. And this one will produce electron, and of course it will form H+. So means this one will form or will have a more positive charge that generates. So to balance the positive charge here, the chloride need to move here, move to this half cell to balance the charge. So at the same time, the potassium ion need to move to another half cell to balance the extra negative charge. Okay, so this is a function of short bridge. Okay, again, because these ions can move from the short bridge, eventually it can maintain the charge, okay, of the cell. Now, for part 3, complete the diagram of apparatus that can be used to measure the E0 of the this dichromate half cell against the SHE. Your diagram should be fully labeled to identify all apparatus, substance, and condition. So you have to put all in. Now, for this one, because it's a partial diagram, the blue color is what I put. So you have to draw the gas electrode, something like this one. So the hydrogen gas with this pressure 1 atm, so it has to push into the half cell, and we use the platinum electrodes here with the acid solution 1 mole per dm cube. Okay, this is for the SHE. And another half cell, you have to draw one plate. This is a platinum plate, and the solution is these three ions. So it's a dichromate, chromium 3, and the hydrogen ion. All these must be 1 mole per dm cube, standard condition. Okay, after that, you just link these two half cells, draw the voltmeter, and that's all. Right, so this is a drawing, complete drawing for this part. And part 4, this one, the E0 of this dichromate half cell is positive 1.33. So from here we know that this is a more positive value than the hydrogen electrode. So means this one will undergo reduction, means these half cell will undergo reduction and the others will undergo oxidation. So reduction means it's a cathode. So now label the negative electrode and the direction of the electron flow in the external circuits when the current flow in your diagram in part 3. So this one is very easy because the dichromate is the half cell that need to gains electron. So means gains electron, and it need to get the electron from another half cell, means the hydrogen electrode need to produce electron. Because this electrode is the place to produce electron, so it's charged negative. So it's negative electrode here because it's produce electron. So the one that gains electron is the positive electrode. So you just put positive sign on this half cell, okay, and negative sign on this SHE. And of course you have to draw the direction. So the electrons is from the SHE to the dichromate half cell. Okay, part D. Table 3.1 is list out a few electropotential that you can use in part 1 and part 2. Later we're going to use that. Okay, and now let's start part 1. What is that? Ethana is oxidized to ethanoic acid in the presence of dichromate ion. Construct the ionic equation for the oxidation of ethana to ethanoic acid using dichromate acid in acidic condition. Calculate the E0 cell as well. So this one you have to choose the correct half cell. For the ethana, we know that there are two half cell or two electrode reactions given, which contains the ethana. This one and this one. So which one we should choose? So because in this question is already mentioned oxidation of ethana, so we must make sure the ethana after reaction will produce electron. Means we must choose this one. Ethana, when it shift to left, it will produce electron and it will form acid. This ethanoic acid. So we must choose the third one, and of course we must choose the first one, the dichromate ion. And of course it's very clear that in the question it say that ethana to ethanoic acid, so you have no choice, you must choose ethana to ethanoic acid, right? Because in this second electrode reaction, ethana actually is from this ethanol, right? Okay, so now this is the reaction. So we need to get the overall equations now. So because the dichromate half cell here is more positive, so it's 1.33, and this one is negative 0.94. So therefore, we know that this one will stay as reduction form, and this one must reverse as I told you just now. So it's reversed and it's get oxidized release electron. So it's something like this. Dichromate, okay, is the same half equation, and for the ethana to this ethanoic acid, so all the equations you have to times 3. So after times 3, then you get this 6 electron. Make sure it's 6 electrons here. Then, oops, sorry. So it's here 6 electrons. So then it can be cancelled out. Okay, after that, you get this overall equation, right? Okay, so therefore you get this overall equation, right, from these two half electrodes reaction. After that, to calculate the E0 cell is very easy. You just use the cathode minus anode. So we know that this one is being reduced, so it's a cathode, and this one oxidized is the anode. So 1.33 minus negative 0.94. So you get 2.27. Part 2. In an ethanol-oxygen fuel cell, the ethanol and oxygens are in contact with two inner electrodes immersed in the acidic solution. The cell reaction of this oxidation is something like this. So means ethanol oxidized by oxygen from the acid and of course water. The E0 cell is 2.01 volt. Oh, this one is quite difficult because you need to calculate delta G, means the Gibbs energy for this oxidation. The difficult part is you need to find the N, means the electrons numbers that involved. So how to get this electron number? So no choice, you must get this one done, right? So we know that the ethanol will oxidize to ethanoic acid. So after that, we have to balance equation. So you start with these two. After that, you have to balance oxygen. Here, it has 2 oxygen. You have to add 1 H2O here to balance oxygen. Then you have to balance the hydrogen. So hydrogen over here is 6, 8. So here also need to be 8. So plus 4H plus. Then balance the charge. Here plus 4 electron. Oxygen now is form the H2O. Then you have to balance oxygen times 2. Then here plus 4H plus 4E. So combine these two, eliminate this one, and eliminate this one. You get this overall equation. This one. So you get this overall equation. The important thing now is what? From these equations, we know that 4 electrons involved. So here is 4. And it's a negative 4 times the Faraday constant, 96500 times the E0 cell. E0 cell is given, right? Substitute into that. After that, you get this value. Make sure you divide this one by 1000, because after you use delta G equal to negative NF E0 cell, the unit is joule per mole. You need to divide this one by 1000 to convert this to kilojoule per mole. So you get this one, negative 776. Okay, that's all. Thank you. I hope you understand.